We see things fall every single day. Keys slipping out of your hand, a pen rolling off a desk. But what's the actual science behind that little journey to the ground? Well, today we're going to get into it. This is the science of freefall. So, to really understand this, we've got to start by tackling a question that's been bugging people for, well, centuries. It's one of those bits of common sense that maybe isn't so sensible after all. I mean, it seems totally obvious, right? If you've got a bowling ball and a feather and you drop them at the exact same time, you just know which one's going to win that race to the floor. But is it really because of the weight? Okay, let's rewind the clock about 400 years. There's this brilliant Italian scientist, Galileo Galilei, and he's looking at this exact same problem. And he decides to challenge what literally everyone thought they knew. He came up with this idea that was honestly pretty wild for the time. He suggested that if you could just get rid of one thing, the air, then how much an object weighs has absolutely nothing to do with how fast it falls. And this is where it gets really cool, this clash between what we think we see and what's really happening. On one side, you've got our everyday experience, but on the other, you have Galileo's incredible insight. And the key phrase, the secret ingredient here, is neglecting air. That little detail changes the entire game. And this was huge, right? It was a major step towards understanding the basic rules of our universe. So if air is the big spoiler, how in the world do you prove Galileo's idea? I mean, you can't just snap your fingers and make all the air on Earth disappear. No, you have to go somewhere that doesn't have any air to begin with. And that's exactly what happened. It just took a few hundred years to pull it off. The ultimate test of Galileo's big idea had to wait until humanity took that one giant leap and landed on the moon. And boom, there it was for the whole world to see. On the moon, with no air to get in the way, the heavy hammer and the super light feather just floated down together in perfect sync. They hit the lunar dust at the exact same moment. Galileo was right all along. Okay, so if we know that everything falls at the same rate, when we ignore the air, of course, then what is that rate here on Earth? Well, it turns out there's a very specific, very important number for that. And here it is, 9.8 meters per second squared. This one number, which physicists just call g, is the constant acceleration for any object in free fall near the Earth's surface. We call it free fall acceleration. And that little squared part? Don't let it intimidate you. All it means is that we're talking about a change in speed over time. To put it simply, for every single second an object is falling, its downward speed gets faster by another 9.8 meters per second. So the speed just keeps building up nice and steady. An object doesn't just fall at one speed. It's constantly getting faster and faster and faster. It's picking up an extra 9.8 meters per second of speed every single second. That's acceleration. All right, so that's what happens when you just drop something. But what if we mix it up a little? What happens if, instead of dropping an object, we throw it straight up into the air? You can picture it, right? It's a journey in two acts. On the way up, the ball is fighting gravity, so it's slowing down, until it just hangs there for a split second at the very top. Then gravity wins, and it accelerates all the way back down. Its speed, its velocity is changing the whole time. But what about its acceleration? And here is a classic physics puzzle. It's a real brain teaser. If something stops moving, even for a tiny instant, how can it possibly still be accelerating? It feels like the acceleration should be 0 too, right? But here's the absolute key. In physics, we often say that up is the positive direction. And since gravity is always pulling things down, its acceleration is constant. It's always negative 9.8 meters per second squared, just like you see here. Even at the peak, when the ball's speed is 0, that constant downward pull is still there. Think about it. If the acceleration hit 0 at the top, the ball would just stop. It would just hover in midair. And if you're a visual person, you can see this whole journey mapped out on graphs. The graph that tracks the ball's position makes this perfect, beautiful upside-down parabola. But check out the velocity graph. It's just a straight line, sloping down. That straight line is everything. It tells us that the change in velocity, the acceleration, is totally, completely constant through the whole trip. So now that we've got the physics down, let's zoom out. Is this magic number, this 9.8, some kind of universal constant, or does it change depending on where you are? Well, it turns out that 9.8 is pretty special to us. here on Earth. That freefall acceleration is different on other planets, it's different on the moon, and it's even different if you go way, way up into space. It all comes down to the mass of whatever big object you're standing on. And this chart really puts it into perspective. Look at the moon. Its gravity is only about 1/6 as strong as Earth's. Now you can really see why that hammer and feather experiment worked so perfectly there. Things just fall so much slower. And hey, you don't even have to leave the planet to feel this. If you've ever been on one of those giant drop tower rides at an amusement park, well, the second that car is released, every single person on that ride, no matter how much they weigh, is accelerating down at that same exact rate, 9.8 meters per second squared. And that brings us right back to where we started. See, all this perfect physics, all this talk of 9.8, has been happening in a perfect vacuum. We've been ignoring that one huge factor that's all around us, the air. And the moment you add air resistance back into the equation, well, that's when things get complicated. And that is why a feather and a bowling ball don't actually fall together here in the real world.